All right, here we go. Everybody up here. Thank you so much. So happy Wednesday. Today is what is today? Wrong day. Today is May 11, and we are covering something called slope fields and Euler's method. It looks like Euler. It is not Euler. It is Euler. We've got one more day of new stuff. Growth and decay is coming up on Friday. That's a bunch of word problems involving differential equations. Our review day is coming up on Monday. This class will be all over 1 week from today. Our final exam is 10:30 to 12:30 Wednesday coming up. Questions on the calendar?
What is that?
10:30 to 12:30, but we're going to expand that a little bit. We'll talk about it Monday. Also coming up, project number 9, the last one is officially assigned. I put it on the tables, so go ahead and grab one. Everybody has a copy of this new project. It's due at the start of that final exam. But it is not a math project per se, and if you have time over the next few days to get it out of the way, then do it, so you're not thinking about it while you're doing final exams and projects and all that other good stuff, right? You can do it anytime you want. I'd encourage you to do it sooner rather than later. Quiz number 6 is going to be due on Monday. I will hand that to you on Friday. It's another take home. And I think that's it for the calendar. All right, speaking of our schedule, the Math Studio coverage schedule has been posted all semester in yellow, and I gave you guys all a bookmark for it, and that schedule goes through the coming Monday. But once final exams start on Tuesday, that schedule is null and void and no longer valid, and is replaced by this blue thing, which is taped on the window here. It's projected here. I'm going to pass it around. Our exam is Wednesday morning at 10:30. So if you are thinking about coming in next Wednesday before the test or anytime on Tuesday, you're going to want to take a photo of this thing as it goes around. Okay? It's this schedule on Tuesday, not the one that's in yellow. So just send this around, take a photo if you wish. And all the folks whose names are on the yellow semester schedule, they're either paid to be in the studio or it's part of their contract, but everybody on the blue paper is volunteering their time. So if you come in Tuesday or Wednesday to work with somebody in the studio, just thank them. Okay? All right, so I think we're ready to jump in here at the top of page 75. Oh, one other announcement. This coming Monday, I'm hoping this isn't a problem for anybody, but I'd love to shift our class 40 minutes earlier. I've got a meeting that I'm supposed to head to at 11:30 on Monday, and doing this will make it so that I can actually go to the meeting. Is this a problem for anybody? Yeah. So I don't think anybody else is in class, but maybe people have other commitments I don't know about. I hope it's not a problem for anyone. If it is, let me know. Okay. And I'll remind you of this on Friday as well. Look at this guy. Yeah, it's like a car salesman right here. All right, so starting on 75. Today we learn a qualitative technique and a numerical technique for studying the family of solutions of an ordinary differential equation. Let's just jump in. We're going to skip this little paragraph on 1 and start with the problem here. At time t equals 0, a tank contains 4 pounds of salt dissolved in 100 gallons of water. Suppose that brine, what does it mean? Salty water. So we've got some salty water containing 2 pounds of salt per gallon of brine is allowed to enter the tank at a rate of 5 gallons per minute. So we've got some salty water coming into the tank, and that solution is all mixed up. So the tank just has this big mixing thing inside of it, and then it is drained from the tank at the same rate, meaning the 5 gallons per minute. So we got 5 gallons per minute of salty water coming in, 5 gallons per minute of whatever's in the tank going out. And what we're going to do is try to come up with a formula that tells me how many pounds of salt are in the tank at any moment in time. That's what we're after, a formula for the number of pounds of salt in the tank at any moment in time. And so what we're going to do is just give a name to that formula. So we'll let Q of t be the number of pounds of salt in the tank at time t, which is going to be in minutes here. And so there's one value of Q that's given to us. Q of 0 is how much? 4, because it says there are 4 pounds of salt initially in the tank, right? But then as soon as we turn the switch on, we've got salt water coming in and the tank getting all mixed up and then salt water leaving, and it's complicated. It's really complicated. And so what we're after is a formula that would tell me how much salt is in there 10 minutes in and an hour in and 5 days in. Just a formula that's going to have T's in it, okay? That's the goal. And I will grant you that this saltwater problem is not all that interesting, but imagine instead of a tank with salt, it's a river with pollutants coming in from a factory. And we're just trying to decide, like, can this river sustain the pollutants? Can it clear the pollutants fast enough, or are there going to be some negative consequences to the, the wildlife that are in that river? You could also think about it in terms of absorption of medication into the bloodstream. Like, your body is able to process drugs at a certain rate, and if you exceed some threshold, you are going to suffer the consequences. So same idea with, stuff coming in, and then it gets processed, and then it gets absorbed or eliminated or whatever. Okay, so here's how we're going to start by writing our differential equation. We're going to write this: dq dt equals, so in plain English, this represents the rate of change of salt as a function of time, right? And so I'm just going to write in plain English that this is the rate of salt that comes in, and then minus the rate of salt out. Okay, so let's start replacing some things. Rate at which the salt comes in. Well, I'm given 2 pieces of information about stuff coming in. I've got 2 pounds of salt per gallon entering at 5 gallons per minute. What I'm interested in, what are the units for dq dt? That's going to be pounds per minute, right? Just copying the units for Q and the units for T in that order. So I'm after some number of pounds per minute. What am I doing with these 2 numbers, the 2 and the 5, to get the number of pounds of salt coming in per minute? We'll multiply them. That's what we're going to do. We're going to multiply them. So let's write. So I'm just going to write some units here. This is 2 pounds of salt per gallon. And then next to it, I'm going to write this 5 gallons per minute. And lo and behold, if I multiply those 2 things, what happens with my units? The gallons cancel, and I'm left exactly with what I want, right? Pounds per minute. So 10 pounds of salt per minute are coming into this tank. Okay, so far so good. The hard part is the stuff that's leaving, because the stuff that's leaving depends on, like, it's leaving at 5 gallons per minute, but how many pounds of salt you have per gallon changes, right? Like, in the beginning, it's 4 pounds for the whole tank, but then as soon as you flip the switch, it changes. And so this is the complicated part. So let's fill it in. Minus. I'm definitely going to be multiplying 2 things together. So I'll get my multiplication. The 5 gallons per minute is the same for the stuff going out. So let's copy that. 5 gallons per minute. And it's got to be the same units for this blank thing. It's still going to be pounds per gallon, right? So let's put some pounds and some gallons there. And our job is to fill in the 2 blanks. At pounds per gallon, what kind of physicsy word are we describing? Pounds per gallon? That's a density, right? So we're looking for the density of the salt in the entire tank, not in the pipe that's coming in, which was given 2 pounds per gallon. That was the density coming in, and it's constant. But we want the density in the whole tank. Okay, let's fill in the number in the bottom. Gallons. How many gallons are in the whole tank? 100, and that's constant. So we can just put 100 right down there. And now what I'm looking for is the number of pounds of salt in the entire tank, which is changing, but which we have a variable name for. That's Q of T. I'll just call it Q. Changing. So do we buy that? That's our density. Q pounds of salt changing over the 100 gallons of water, and then times the 5 gallons per minute. The 4 is embedded inside of the q. The 4 is just a particular instance of the q function. Yeah, so well, maybe it's better, as Yanni said, q of t, just to really highlight this is a changing thing as time passes. Okay, so then our simplified equation, we'll just rewrite it, but without all the units. dq dt equals, so 5 times the 2 is 10, minus, we'll simplify here, the 5 and the 100 make it 20. So 1/20th of q, we buy that? Okay, so that is our differential equation that describes this salt system. And now we're going to solve it. Any questions on the setup? Okay, so let's come down here, number 2. We're going to solve it. It's written out there for us. And then the q of 0 equals 4 is the initial value, right? So IVP was initial value problem. Okay, we're going to, pretty much the only technique we have for solving differential equations is to separate the variables. Get all the q's on the left-hand side with that dq, all the t's, which there aren't any, on the right-hand side with the dt. And the only thing that we're allowed to do as we move terms left and right is which operations? Multiply and divide. That's all we can do, right? You cannot add a 20th q to both sides. We got to multiply or divide. And that seems problematic because the right-hand side is firmly a subtraction, but in worst case scenario, we could divide both sides by the entire right-hand side. So let's do that. So the left-hand side is now over that 10 minus 1/20th of q equals, on the right-hand side, just the 1 dt, right? That's it. Everybody see what we did? Divided both sides by the right-hand side. So all of it went downstairs on the left. Okay, well, it worked. It is separated, right? All the q's are on the left. All the t's, there aren't any on the right. Okay, and then in front of both sides, we put our integral symbol. So we've got 2 integrals to do. I'm going to take care of the hard one on the right-hand side. That's a t plus c. Thank you. I'm here all week. All right, so the left one. That's the one we got to work on. The left one is a u substitution. Choices for you. The whole denominator, and when you let u equal the whole denominator, it's going to be a 1 over u. So 1 over u becomes what when you do the integral? It's ln. All right, so I'm going to put my ln of the whole thing, 10 minus the 20th q. But if we let u equal this whole thing, then what is du? Is negative a 20th, right? And it's just the constant. And so I don't know if we remember all the du stuff we did, but that's going to end up getting flipped over when when it pops out. So it's going to be a negative 20 in the front. So there is lots of work we didn't write down embedded in that negative 20 in the front. So a full-fledged u substitution. You don't need to do it in your heads like we did, but you do need to be able to do it. Okay, so there we go. We've solved our differential equation. We can, what can we do? We can solve this guy for the letter q, which is the norm. It's like to solve for the dependent variable. Some folks ended up running into some difficulties finding the value of c at the end of the problem. And sometimes it's easier to find c early in the problem. Let's just give it a shot. You can find c anytime from this point forward. All we know is that q of 0 is 4, right? So the q is going to change to what? The q is the 4 and the t is 0. Okay, so let's plug that in and see what we get. So negative 20 ln 10 minus 20th of, we said q was 4 and t was 0. Okay, so a little bit of arithmetic here. So what do we get? ln, let's see, that's a fifth. So is that 39/5, I think? Somebody check me on that. Is that right? No, 49/5. Yes? 49. Thanks. Okay, so there's our value of C. So then I'm just going to rewrite this guy down here, but change the C according to what we just found. Question so far? It was for that one moment, but yeah, now it's back to T. Okay, again, trying to solve for Q. The rest of this is going to be like pre-calculus algebra type stuff. Not to say it's not work. I mean, there's plenty of opportunities to make mistakes as we solve this equation for Q, but there's no more calculus to be done, I should say. Okay, so solving for Q, let's divide both sides by that -20. And while we're at it, I see a -20 here in the C part. So I'm just going to split this guy up so I can cancel that -20. So I'm imagining -20 underneath both terms on the right-hand side. So we get ln 10 minus 1/20th Q equals, so dividing by -20. And then dividing by -20 makes us a plus ln of 49/5. Is that all right? Divide both sides by the -20. And then both sides get hit with E, right? We're trying to get our hands on Q, which is still pretty well buried right now. So E both sides. So the left-hand side is just the 10 minus the 20th Q. Right-hand side is just E to everything that we had before. Now on the right-hand side, I see an E to something with ln inside of it. And I feel like if we work, we can get those two guys to be right next to each other and cancel. So I think this is a good moment to try to just focus on the right-hand side, clean it up a bit. So copying the left-hand side for the time being. We know we can take this E and split it up over that plus sign. So E to the -t/20 times E to the ln of 49/5. Is that all right? Which that part is just going to become 49/5. That's the goal, is to make it so we can cancel the E and the ln. But first we split it. So one last time copying the left-hand side. And then 49/5 E to the -t/20. Okay, and then just two more steps to solve that last equation for Q. So we're going to come down here now. So we'll subtract the 10. So subtract 10 both sides. And then finally, multiply by -20. So let's do that. Q equals. Okay, so -20 coming in and distributing. So -20 times this 5 makes a -4 times that guy. So is that, I think, -196? Somebody check me on that. And then -20 times the -10. Did I do that right? Yeah, okay. I'll call this Q of t here in our last line. Okay, so there we have it. That is our solution to our differential equation. And that's the formula which predicts for us how many pounds of salt are going to be in the tank at any moment in time. So for example, if we plug in t equals 0, how many pounds of salt were we given in the tank at that moment? 4. Well, this had better predict that we're going to have 4. If we plug 0 in for t, what do we get? We get 4, right? Because that e to the 0 is 1. So 200 minus 196. Okay, so that's great. It confirms what we knew already. But for example, 1 minute into this experiment, we didn't know how many pounds of salt were going to be in the tank, but we could find it, couldn't we? Somebody with a calculator, can you just plug 1 into this thing for us here? Do we expect the number of pounds to be increasing or decreasing here at the beginning? Initially, there were 4 pounds in the entire 100 gallons of water, and the salt water coming in is a lot saltier than the stuff that was already in there, right? So we're going to be increasing. So Q of 1, how much is it? 13.5. Can somebody? Well, so it gets mixed up really thoroughly as it leaves, and yeah, it's diffused completely the moment it enters the tank, which is an assumption. Yeah. Anybody get Q of 2 for us here? What I'm now interested in, I mean, I still believe it's going to be increasing here. Do we think it's going to increase by as much? I mean, we know that Q of 0 was 4, so we gained about 9.5 pounds in that 1 minute. Did it go up by more or less? So did this go up more or less? Went up 9.5, and the was a little bit less, right? Like 9.1. Does that make sense? Like the least amount of salt in the tank is right there at the beginning. And then a minute into this experiment, the water is saltier than it was at the start. And so, yeah, the brine stuff is coming in and making it saltier, but it's just, they're not as far apart a minute in as they were at the start of this experiment. And then Taylor, what did you say about the long-term behavior? Okay, so Taylor is saying that eventually all the water in the tank is going to be the stuff that's coming into the tank. And we know the stuff that's coming into the tank, it has how many pounds per minute? It was 10. That was the 10 we calculated here. So Taylor is saying that eventually all the water in the tank is going to be 10 pounds per gallon. Yes? Okay, so 2 pounds per gallon. Yes, all of it is, yeah. So so it's coming in at 10 pounds per gallon and leaving at 10 pounds per gallon per minute. 10 pounds per minute in, 10 pounds per minute out. And so can we come up with an intuitive answer to this, and then we'll check the formula? Isn't it going to be 200? Because there's 100 gallons in the whole tank, and the water coming in has 2 pounds of salt per gallon. So 2 times 100 is 200. Does the formula predict the same 200? If t gets really big, e to the negative really big goes to 0. So that first part doesn't do anything. So the 200 kind of confirmed, like our intuitive 200 is confirmed by our formula. Okay, that's good, good, good. Next page. So we're going to draw something called a direction field or a slope field. This entails drawing little tangent lines of the appropriate slope at a bunch of different points. Let's try it. So the last column here is dq dt equals, and it's just a differential equation we created. The first column has some values of t, 0, 50, 100, 150. Second column has some values of q. The first 4 all 100s. So let's start plugging some stuff in and getting some numbers here. If we plug in t equals 0 and q equals 100 into this expression right here, what do we get? So there's no t's to plug in. So 100 for that q gives me, is that 5? Right, 10 minus 100 over, yeah, 10 minus 5 is 5 is good there. If we plug in 50 for t and again 100 for q, what do we get? Also 5, because there are still no t's in there, and so those first 4 entries are all 5, and the point is because this happens to be a differential equation with no t's on the right-hand side, it doesn't matter what t is. But if there were t's floating around on the right-hand side, you'd imagine these numbers would be changing, right? Okay, so I've left a blank for the rest of the t's because the t doesn't matter. So if we plug 150 in, I think that's 2.5. If we plug 200 in, that's a 0. Plugging 250 in, it's a negative 2.5. And plugging 300 in, negative 5. Good. So here's what we're going to do. We are going to come over into this picture right here. We're going to pick this point right here, 0, 100. 0, 100. So that's kind of where we put the origin here. But anyway, that's the point 0, 100, yeah? T is on the horizontal, Q is on the vertical. And at that point right there, we're going to draw a little tiny line segment whose slope is 5. And the reason we're drawing a little tiny line segment whose slope is 5 is that the differential equation says dq dt equals, and dq dt we know is slope, right? So all we know is that at the point 0, 100, the q function, which we're thinking about, has a slope of 5. And so you're just going to draw a fairly steep uphill line segment at that point right there. And then at the point 50, 100, it's also a slope of 5. So the point 50, 100, you go find it. Another slope of 5, so parallel to the one that we first drew. And the same thing at 100, 100, and 150, 100. Okay, and then the next tangent lines, let's see. If we go to any value of t, 150, the slopes are going to be 2.5. So steeper or less steep? Less steep. And so up at 0, 150, not as steep. And then we said it doesn't matter what the t's are. So just go straight across and draw those same little tangent lines. What kind of tangent lines at 200? Flat, horizontal, right? Slope is 0. So at 200, little tangent lines that are horizontal. Yeah, and then at the 250 line, diagonal the other direction, downhill now, right? So a slope of negative 2.5 up here. And then at 300, steeper or less steep? Steeper, still downhill, but steeper, so slopes of negative 5s, so pretty steep up here. And so the idea with this diagram is that we are trying to imagine curves that we can draw onto that picture that have those things as little tangent lines. And so you're just imagining trying to like trace a curve as it follows the flow established by all these tangent lines. So for example, if I decided I wanted to pick a curve that started there, well, at that one moment, the slope is positive 5. So it's going to the right a little bit and up pretty, a bunch. And so maybe it's, like up here. Now, I don't have a little tangent line drawn at that new spot, but it's probably not far from the tangent line that I just left. But it is heading towards these lines up here that are not quite as steep. And so you imagine, kind of trying to draw things that essentially have these guys as little tangent lines. And hopefully you can start to see curves that look like that, just following the flow. And if instead of starting up there, it had started down here, well, I don't have information down there, but what do you think? Increasing or decreasing? Increasing. Concave up or down? Concave down. Will it cross the first green one? The fact is they'll never cross each other. And so this guy, like they're both kind of honing in on that 200 horizontal, but they never hit each other. And if we tried to start with one up here at the 250, increasing or decreasing? Decreasing, concave up, right? And so we can just start to think about all these different curves And the reason we have so many of these is that we know that solving differential equations involves a plus c. And so we've just got lots and lots of different plus c's. Right? What if it started at the 200? It started there. It's going to be perfectly flat. It's just going to move to the right and not up or down at all. And then it'll encounter another little tangent line that says, hey, do the same thing. And so we've got that flat one right in between. And we can draw this without solving any differential equation, right? We just did all the work of solving that differential equation and getting q equals the negative 196, right? All of that work. But we can get a sense of what the graph looks like without doing any of that work. We established that it heads towards 200. Do all of these curves head towards 200 in the long run to the right? They do. And our function started at q of 0 equals 4. So I guess that's someplace down here, right? 0, 4 is down there somewhere. And we know it's going to be increasing, and we know it's going to be concave down, and we know it's going to level off at that 200. And we established all of that without actually doing the work of discovering that it was negative 196 and then all of that stuff. And so solving differential equations is hard, just like finding antiderivatives is hard, but drawing slope fields is easy. And if you are just looking for qualitative information about the solution without actually going through the work of finding the solution, draw some slope fields, right? You can tell increasing, decreasing. You can tell concave up, concave down. Sometimes you can tell sort of asymptotic limiting behavior. So that's the idea of slope fields. Can somebody describe, like, I mean, I bought the whole, you know, like increasing and not by as much. That's what we discovered by looking at our particular function. But what's going on up above? Under what condition would the amount of salt in the tank be decreasing? That's it. If it started at a higher concentration than it's flowing in, right? We started with 4 pounds of salt, but imagine we started with 300 pounds of salt. Then it is saltier in the tank than the actual water flowing in, and so the salt leaving the tank will go out faster. More salt will go out than will come in, and so the amount of salt will decrease, still tending towards 200, but from the other direction. Same situation, but imagine you're out doing skydiving, and ignore the parachute part, but we're just going to free fall until what happens? Well, before, right, terminal velocity, right? So if you just jump out of the airplane, your initial velocity is 0, and then you speed up, speed up, speed up, but we know we're going to reach terminal velocity. Do you see it? What number is it in this picture? The 200. And so you start with a velocity of 0 or 4 miles per hour, and then you speed up, speed up, speed up, but leveling off to 200. Same idea. What poor circumstance would the skydiver be in if they were above that? They were shot downwards out of the airplane at a speed faster than terminal velocity. But what would happen? They would start to, they would, wouldn't they slow down?
Yeah.
Like it's very strange to think about that you could be dropped out of an airplane and actually slow down. But if you are shot faster than terminal velocity would have you go, then you are going to slow down until you level off at terminal velocity. Okay, so I think that is that. Just one last piece of vocabulary here. The equilibrium solution is just a place where the thing never changes. What was it in our case? 200. That was the equilibrium solution. Equilibrium solution has to be represented by a horizontal line, nothing else. If you have 200, if you started this process with 200 pounds of salt in the tank, it would remain 200 pounds of salt in perpetuity, right? Nothing would ever change. Okay, so there are some slope fields down below. You're gonna, oh, and of course, by the way, you know, so we drew however many little tangent lines over there, what, for 20, we drew 20 little tangent lines, but you'd have a more accurate sense if you drew 200 or 2000, right? And that's tedious for us, but piece of cake for computer software. So here are some computer generated graphs, very easy to make, and you can find free websites that you'll just type in the equation and it'll say, hey, here you go. How many lines do you want? So you're going to come back, but we're going to do part of this thing in the activity together. Let's jump up to this. Let's jump to 78. So here's the process that we're introducing here on 78. We've looked at our slope fields. We know we can get this kind of qualitative information, increasing or decreasing, concave up or concave down. But we really couldn't say much specific besides that, right? Like we couldn't say, oh, Q of 1 is going to be about 13.5, not from looking at that picture, yeah? Like I want to know, can we say something more specific about Q of 1 and can we approximate it at 13.5? We're pretending we don't know the formula. All we have is the differential equation and maybe the slope field. So let's fill in some of these blanks on this page. So given that the slope of that diagonal line is 2, if delta x is 3, how much is delta y? It is 6, right? Because we know delta y over delta x. So this is for sure 6. And so since delta y over delta x is m, if we were so inclined, we could solve for delta y. What is it equal to according to our first equation? It is, but in terms of those letters over there. M times delta x, right? Just multiply by delta x. And we can confirm that in our case. If you multiply the slope by the delta x, what do you get? 6, great. So there's a formula that we're going to use. So here is a complicated picture with lots of blank lines in it. We're going to fill them all in. So here's the idea. We've got some differential equation. The differential equation is given by this thing up here in yellow. dy dt equals some function. Now f of t comma y is something you'll spend a lot of time with in Calc 3, which is multivariate calculus, right? But that is just a function with two variables in it, t's and y's. In our formula, we just had q's, right? The right-hand side was, what was it, 10 minus 1/20th of q, but just as well could have had a t inside of there in addition to the q. And so we've just got a differential equation equal to some generic formula with t's and y's in this case. Okay, and so the solution to that differential equation is this guy right here in purple. So I'm just going to write that this is the solution. And we are thinking of q is equal to the negative 196 e to the dot, dot, dot. Oh, goodness. Thanks. But all the analysis we're about to do assumes that we don't have the formula negative 196e to all this stuff. All we have is the original differential equation, right? We just got lucky. I gave us one that we could solve and get the negative 196. So everything we're doing assumes we don't have that formula. But we're going to try to approximate values on that formula without actually having the formula. So the next piece of info we're given is this point right here. We've got some starting point. In this setup, it is given as t0 comma y0. It's in the little paragraph above the picture. That's that particular point. It's a starting point. What was it for the salt problem? What comma 4? 0 comma 4. So we just have a starting point, and that's it right there. And so what we're interested in is to be able to move from that starting point in blue over to some other point on the solution curve. So some point that's a little bit to the right. How far to the right, we'll fill in some symbols in a minute. But without the curve, well, we can't, when we don't have a way to get that. But also drawn in here is a tangent line to the curve at that one blue point. And if we have the equation of that tangent line, then for sure we could find the coordinates of that red point that's right above the red point we're interested in. Yes? Right? Because we will have the equation of that tangent line. And so the point here is that if you haven't gone too far from getting to the blue to the red, if you haven't gone too far to the right, then the two reds are probably not going to be that far from each other. And by that, like this is really blown up, but if you imagine that you've only gone over like 0.01 or something, then the 2 points are nearly on top of each other. So this is the idea. We want the point on the curve, but we don't have the curve. We're going to settle for the corresponding point on the tangent line, right? And so the goal is to find that point on the tangent line. That's what this whole method is about. Okay, so let's start filling in some of these blanks. Let's start with number 2 down here at the bottom. What symbol for that distance represented by number 2? That's t sub 0. That's the original t value. How about number 3? That's the y sub 0. Okay, now we're looking for a symbol for number 4 here. It is a small change in t. Delta t seems like a reasonable symbol to put there. Okay, let's fill in number 7 right now. 7 is the actual value of our formula that we don't have, right? That purple big formula. The formula is named y. So this guy right here is really y of what? It's the original t0 plus the delta t, yeah? That's the actual value, the thing we want but can't have. So I'll put the word actual here, actual. Number 6 is going to be an approximation. So I'm going to write the same y of t0 plus delta t, but it isn't the actual value. This is our estimated value. We want the actual, but we can't get it, so we're just going to estimate. Y naught plus delta y. Yes, it is going to be y naught plus delta y. So right now this is just kind of an English, like here's what we're after, and then we'll do the specifics of the formula down below. Okay. And again, the value of this 6 and the value of that 7 are hopefully not too far apart, right? As long as delta t is not too big, then probably 6 and 7 are close to being equal. Okay, let's start filling in some more stuff here. I am going to draw this triangle right here. So that's a triangle that goes right along the tangent line. The horizontal line segment, what symbol is this horizontal length? That's a delta t. What symbol for the vertical length? That's a delta y. It's the same picture that we had up above. This is just our triangle embedded in a more complicated picture. So delta y is what we're calling that number 5. Okay. And then I think the only other blank we've got is this number 1 up here. It says the slope of this line is, okay, so that is a tangent line. And we know that the tangent line has a slope equal to the derivative at the point. But according to our differential equation highlighted in yellow, the derivative is given by the formula f of t comma y, which we don't have. This is just generic. But the derivative is the slope of the tangent line. And so f of t comma y is the slope of the tangent line. But more specifically, it's not any old t comma y. It's this blue t0 comma y0. So the slope of that line right there is just f of the specific t0 and y0 that we start with, right? Okay, so all we got to do is get a formula down here, and then you guys will start using this theory that we're developing. Okay, thinking about this picture right up here at the top, we know that the delta y is just m times the delta x, right? So I'm going to copy that guy down here, and then we'll start filling it in specifically. So that delta y up there is m times delta, okay, it's not delta x in this picture, what is it? Delta t. Okay, so it's m times delta t. And the m for that triangle is, it is, but I want to call it this f of t0, y0, right? That's the m, that's the slope of that particular line. So the m becomes this thing up here in black, f of t0 comma y0 times delta t. Okay, I think we're ready to start filling in some stuff in the bottom equation. Okay, starting with number 8. What we were interested in was the actual y of t plus delta t. So I'm just going to abbreviate that with the word actual. What we're going to do is write a formula for our estimated thing, which at 8 is just the, I'll highlight it here, that's this. It's just the next number in the list. It's not, yeah. Is something over 8? Yeah, it's just numbering it. Okay, so instead of actual, which we can't get our hands on, we're going to write a formula for the estimated. So that's here in blank number 9. And to get the estimated value, what we are going to do is add this number 3 and that number 5. Buy it? The estimate here is just the value of 3 plus the value of 5. Yes? Okay, so let's write that here. So where are we now? Okay, so the 3 was y0 plus the 5 is a symbol. I'm going to kind of write over our blanks here, but y plus delta y, that's the 3 plus the 5. Okay, with the y0 plus delta y. And the last piece of this puzzle is that delta y is given by this formula right over here. So all we're doing is changing that delta y according to this f of t0, y0, delta t. So here we go. Y0 plus, and then instead of delta y, this stuff in green, f of t0, y0, delta t. Okay, so I grant that this is a lot of symbols, but I'm hoping that without getting lost in the symbols, we buy the idea. We can't find the point on the curve because we don't have the formula, but we're going to find the point on the tangent line by using this formula here, okay? And hopefully they're not too far apart, the 2 points. So let's just take a look at the table on the next page, which will make things a lot clearer. So here, number 5, that process that we just talked about where we go from one point on a tangent line to another tangent line point is called Euler's method. We're going to use a step size of 0.1. That's the stepping to the right. That's the delta t in the formula that we just talked about. It's delta x in this table. And the differential equation we're interested in approximating the solution of is this y prime equals y minus x, which, by the way, even though it's really simple looking, it is not separable, and we do not have the tools to solve that thing. So we can't come up with a formula at this stage that says y equals blah, blah, blah with x's in it is the solution. So all we can do is this approximation idea. Okay, so we are given y of 0 is 2. That's our starting point. We are interested in finding y of 1. That's what we're after. We're going to start at the point 0, 2. We're going to gradually shuffle our way to the right until we land at the point 1 comma some estimate, okay? So let's take a look at how our table works. First column is I. It is just counting, starting at 0, and then we'll go as far as we need to go. The next column is x sub I and y sub I. The initial point is what? 0, 2. So that's right up here, okay? So we just fill in our initial point right there. Then we do this calculation in yellow. It says you take your y and you subtract your x, and that's the derivative, which in the last picture was slope of a tangent line. So when we do y minus x here, what do we get? 2. There. So 2 is the slope of that tangent line. And you remember on the previous page, we took the slope of the tangent line and we multiplied it by delta t, in this case delta x. So we're going to multiply this guy by this guy, and we are putting it right here. So 0.1 times the 2 is a 0.2. That 0.2 represents the change in the y. You started with a y of 2. You are changing by positive 0.2. What do you land on? 2.2. So all we're doing is taking the original y, adding the change amount and that 2.2 is the new y. And that 2.2 starts the next row. So you take your previous y, use it in your next row. How about the x? We started at x was 0. What's the new x? Yeah, so the x's are just going up by 0.1 every time. The x's are really easy. So starting at 0, going to 0.1, and that's there. Yeah, so the x's are really, really easy. You could fill in all the x's right now if you wanted to, because they just increase by the same 0.1 every time. Let's do one more row together, and then you'll pick up with your neighbors here. We've got our current x and y, 0.1 and 2.2. Differential equation says y minus x. So what do we get when we subtract? 2.1, just there. And then we are taking the 2.1 and we are multiplying it by the delta x. That is always what we do. We take our 2.1 and multiply it by 0.1 in this case. So, which one? The x calculations are just, yeah, they're just kind of in the middle here. I mean, honestly, you don't even need them. Like as soon as you know it's a 0.2, 0.3, 0.4, that's more detail than we need. Okay, you take your 2.1, which we calculated, multiply it by the step size, which is 0.1 all the time in this problem. We get 0.21. That 0.21 is how much you are changing from your old y to get the new y. What was the original y in this row? 2.2, and we are changing by positive 0.21. And so we get 2.41. Where does the 2.41 go? That's the next y, 2.41. What's the next x? 0.2. Okay, you are filling this table in until eventually you land on what x value? 1. That's the goal. So you got to keep going. Right now we're at 0.2. You got to keep chugging through these calculations until we get to x equals 1. Okay, so let's see how far we can get. Once you filled in the table, go back to some of the activity questions that we skipped. We'll walk around.